All right, getting situated. My schedule. Hold up a minute. Here it is. I didn't test this. Well, we'll just have to do it this way. Does this work? No, it doesn't. Oh no. Please wait, system processing. Aha! Business. So now if I do this with one swift... Oh, it works! Oh my gosh, okay. Alright. Hey. Feels just like... Thanks, Colin. I just read your delay test, if that's what you're asking about. There's a substantial one. It's like a couple minutes. All right, so I'm going to get started. Welcome. I hope this works. This is our first go at the thing. I hope it's better than WebEx. So, yeah, things have been a little weird. I'm really sad that I'm not able to lecture with you guys in person. It's so much fun to teach this class and run around and have our board games and stuff. But we'll have a different kind of fun for the rest of the semester, which it's kind of exciting. It's a little bit chaos, and I kind of like chaos, so we'll have fun with it. It's going to be a little weird. I don't have a good setup to see the chat and the lecture slides at the same time. So, but when we take little thought experiment breaks or whatever that is, I will go check the chat, see if you guys have any questions, or if you're just loading it down with your Kappas and your Pog Champs. Anyway, here we go. So, Project 3 is out-ish. I don't think it's quite out yet. It'll probably be out a little bit later today. Project 3 is historically the difficult one. Why? Because it's trees. And why are trees hard? Because recursion's hard. So, get started really early on that. On Wednesday, when I do this again, I'll go over Project 3 a little bit so you can get a sense of how to digest the project description and kind of what we're expecting you to do. Class is online now. You can probably tell because this is coming at you through a web browser. Or your phone. Oh, I hadn't even thought of that. So yeah, maybe you're on your phone. That'd be weird. So I got... See, it's my first day streaming class, so I got help from an artistic friend. So he's going to help us lecture today. I also have my buddy. This is one of my teaching assistants. He's thankfully not a grader, but he's very big, and he's very friendly. And he's had some catnip, so he's very high. Okay. Not that I condone herbal substances. Okay. All right. He's wants to go back to his herbal substances. All right. So let's get to the actual stuff. It's really weird to lecture to a wall, but hey, let's do it. So let's do a little bit of review, and I will go look through the YouTube questions and stuff like that. I think if you're watching this in the future, you will be able to see the chat as it scrolls by and all the trolling that's probably happening. But also you'll be able to see the questions as I answer them and stuff like that. So hopefully this format works for you guys. But anyway, so what is the height balance property? Way back in the dawn of time, when we were still meeting in person, we talked about the height balance property. We haven't had an actual lecture for like 2 weeks, so I know it's been a while. But what is the height balance property? See if you can reach back in your dusty brain cabinets to figure out what the height balance property is. How does a node violate it? So when we talk about balancing binary search trees, particularly AVL trees, we're looking for nodes that violate this height balance property. So how does a node violate the height balance property? And it's actually not the most straightforward question. It's easy to kind of mess this one up. So think about that for a few minutes. What is an AVL tree? So the height balance property describes a node. So the height balance property is for a particular node. So how do we say that a tree is an AVL tree in terms of the height balance property? Also, what is trinode restructuring? And there's a few things that you should know about trinode restructuring. How to do it is kind of probably the one you fixated on, but also why do we do it? And how do we express that in terms of the height balance property? And how imbalanced can an AVL tree get? So remember, we're trying to balance these binary search trees because if all of the nodes go in one direction, we basically end up with a linked list. And so we have this very fancy data structure that's not giving us any better performance than a linked list. So we want to keep the tree pizza slice shaped, and we do that by balancing the tree. So how imbalanced can an AVL tree get? So think about that. You can pop your answers in chat. I'm going to go look at chat and see how... Ooh. Boop. So yeah. FF. Oh no. The emojis are worse. Sure. Super chat. Yeah. Can you guys donate? No. Please keep your money. I don't even know how that works, and I don't want to know how that works. Oh my gosh, the delay. Oh no, okay, the delay finally got to questions. Can we get an F in chat for being... Thanks, Octopus. All right, well, these are super constructive, as I might have imagined. Okay, so let's go over the answer to these. So the height balance property is... a node is considered balanced by the height balance property if its left subtree and its right subtree's heights differ by at most 1. And so what that means is that if I look at the longest path from my left child all the way down to the root, to a leaf, and the longest path to the right child all the way down to a leaf on the right hand side, those paths will differ in length by at most 1. So a node violates that when one of its subtrees is shorter or longer than the other subtree by more than a depth of 1. What is an AVL tree in terms of this? An AVL tree is a tree where every node in the tree doesn't break the height balance property, adheres to the height balance property. So then, if you look at an AVL tree, or if you look at any binary search tree, and you have to answer the question, like on an exam, is this an AVL tree? You would go through and you'd look at all the nodes and say, does the left subtree and the right subtree, do they have heights that are within 1 of each other? And you have to do that for all the nodes in the tree, not just the root. It's an easy trap to fall into to be like, well, the root's balanced, so the whole tree's balanced. No, you can have some node somewhere that's imbalanced, and that bad apple spoils the whole apple tree bunch. And so because of the height balance property being what it is, an AVL tree can at most only have like one level of unpizza-ness in its overall structure. It's only going to be like a little bit out of shape for how triangular it is. All right. So one thing that really stinks about this online version of life is that there's not as much ability for us to have discussions and try to think through these riddles. So what I'm going to work through is I'm going to give you guys a challenge, a riddly challenge, and I'd love if in chat, hopefully you guys can try to work out the answer to this puzzle, or just actually try to think through it, because the harder you think about this riddle, the more interesting and the more engaging the answer will be. So to help you stay awake I'm sure you're probably like covered in cuddly animals in a nice warm place. In order to stay awake while we do all this stuff, try to actually figure out and solve this problem. And so today, also I didn't mention, we're getting help from our good friend Bob Ross, because we're going to be painting some happy little trees. It's maybe not the most comforting time in the world, but today we're going to do some happy trees. So here's a problem with AVL trees. The problem with AVL trees is we're being really strict and we're being really judgy about what shape they're in. And so this idea that we have to keep the tree very, very tightly balanced so that one side can only grow one level above or below the other side means that we're going to have to do a lot of this trinode restructuring to enforce this. The trinode restructuring is keeping things in balance and enforcing the height balance property. The problem is that we have to do a lot of it in order to keep the tree that strictly balanced. We have to keep a good eye on it, and we have to do this trinode restructuring a lot. And for the height of the tree, the trinode restructuring is only big O of log n, because each trinode restructuring is a constant set of operations. If you code it out or find the code for it, you find that there is really no loop. If there's a loop, it only executes 4 times. So trinode restructuring is constant, but you might have to do log n trinode restructurings, which is maybe not ideal per se. So what we want to do is say, well, let's try to limit the number of trinode restructurings in there. If we have a ton of data, we might not want our inserts and our removes, because that's what would cause a trinode restructuring. We wouldn't want those things to be logarithmic in time. We'd want them to maybe be, they're going to be logarithmic, the insert, potentially, in the worst case, because it has to go down to the bottom of the tree. But we might not want to be doing all this trinode restructuring. So let's be a little bit more flexible. Let's come up with a tree that's more friendly, that we're not going to be so strict about it. Like, live your best life, tree. And we're going to put some restrictions on the tree, but we're not going to keep this rigid, like, one level of difference. We're going to let it kind of grow more the way it wants, and then occasionally have to go around and make some small changes, which sounds really like, ooh, groovy and fun, but it actually turns out to be a really hard data structure. So, now I'm going to give you, if you're watching this in the future, you can just kind of scroll through the YouTube video until the slide changes, or I come back from the YouTube chat. But discuss, how would you design a tree that lets each node's, one of its subtrees can be twice as tall as the other subtree. At most twice as tall as the other subtree. Remember, AVL trees, they're really, really restricted. You can only have one extra bump out level in one direction or the other. So we're going to be more flexible now. Try to think, what kind of rules would you put into place? What kind of system would you put into place so that each node's say left subtree is either at most twice as tall as the right subtree, or twice as short as the right subtree. And I'm still doing the left and right backwards. But how do you do that? What kind of things could you put in place? And then that means that if we're letting one subtree grow much more and to a level that it's twice as much and not just one more or one less, that means we're going to do substantially less trinode restructuring, because we're going to kind of let the tree look a little bit less pizza slice shaped, and it's going to be a little bit more jangly. I'm going to go look and see if you guys have any burning questions. We're collecting trees. It's true. What if I recalled a super chat? Can I use the bathroom? No. F for the riddles. You guys, I think you're overusing the F meme. You're not paying respects to the riddles. Nothing's happened to the riddles. Yes, lectures will be at 1 p.m. rather than 4. Because I'm not going to give the same online lecture twice. What I'm going to do, though, is I'm going to hold my office hours at 4. So you can watch the... Hopefully you'll find time to watch the lecture before my office hours, and then you can come ask me questions on Discord in person. So that'd be fun. Do I have any merch? No. I might need to make some Jules shirts, though. All right. These are all very productive questions. Wouldn't tree... Oh, Jeremy actually made something substantive. Wow. Wouldn't the tree be one node on the left of root and a full subtree on the right or something? So... Oh, I need something to draw. So I'm getting a tablet to draw tomorrow. So next class I'll be able to draw better. But it's coming in the mail. It's hurtling towards me at the speed of a large truck. So the idea is if I'm a node, if my left subtree is 4 tall, meaning it has the path length from that tree to the deepest leaf on the left-hand side is 4. If it's a valid tree, this new tree that we're making, I can have a tree on the other side that is 8 deep or 2 deep, and I'm still valid, right? That would not be an AVL tree, because the AVL tree would be, if it was 4 deep on one side, it could only be 3 deep or 5 deep on the other side. But here we're trying to be more flexible and say, if it's 4 deep on one side, then it can be as much as 8 deep on the other side, or as shallow as 2 deep on the other side. Can we just compare the height of the left and the right? So sure, you can definitely have variables that are on each node that says what the height of that particular node is. And in fact, when you're doing an AVL tree, you absolutely need to have those heights there so that you can figure out who Grandmama Z is. For this particular tree, you could know whether or not a tree has obeyed, like whether or not it has broken your double distance property. But then how do you enforce it? Where do you go? So say the one side has become 9. How do you go? You have to go find the 9? Like, how would that work? Save the lowest height on each branch. Greetings from the algo stream. Hi, Krez. Recomputing height might kill performance. So, you can, when you're doing an insertion, you're only going to increase the height of all of your ancestors. In the worst case, you increase the height of all of your ancestors. If you're the new deepest node, then in the worst case, you have to walk all the way back up to the root and change all of those heights. But if you might not, a lot of nodes when they're inserted don't increase the height of any of their ancestors because they're not the deepest leaf in the whole tree. There's actually like some fun math there that shows you that that's very infrequent that happens. What else did I say? Any other suggestions? Dynamic array. Not yet. We're getting there, but I'm glad you're still thinking about dynamic arrays. This is still going to be a linked structure, incidentally. Okay. So let's keep brainstorming, but I'm going to give you some more. I'm going to walk you a little bit, some more clues. So how do we know when to fix an unbalanced tree? You guys already got that. You nailed it. You have to look at the heights. But maybe we can be even more clever than that. Also, how do we figure out where to fix the tree? So, the question is, like, so if I have one subtree that's height 4 and one subtree that's height 8, I could probably make... I probably don't want to make the shorter subtree longer, right, because that would hurt performance. I probably want to make the 8 subtree 7 somehow through some series of rotations. The problem is, though, you could come up with a tree where if I have a completely full subtree of size 8, or you could come up with like a really antagonistic tree that in order to get everything shifted around to lower that height of that subtree that's depth 8, to get everything shifted around to maybe like pull some height over into the other side and shorten it. So go from 8 to 4 to maybe 7 and 5 to kind of pull that node weight over. So that's interesting. How would we fix it? It's pretty challenging. And also, how can we use trinode restructuring? So trinode restructuring is a rebalancing procedure, but it only operates on like one little subtree. AVL trees, and then that's when you go find Grandmama Z. Who is our Grandmama Z? That's another part of this riddle. Like, which node is the one that we're going to do the restructuring around? And I'll add to the riddle and say, we only need to find at most 2 nodes to restructure. We're only going to do at most 2 restructurings for any operation. So there is potentially only 2 Grandmama Z's in this new tree that we're figuring out. Remember, because we're trying to make it really relaxed so we don't have to do a lot of trinode restructurings. So in this case, how do we design a tree so that the sides can grow to this double length, but also we only have to do at most 2 trinode restructurings to fix it? We have to be very precise about knowing when things get out of whack. We have to go and like very, very easily go, oh, this one's problematic and this one's problematic. So, all right, let's see if you guys have any questions. Going back to the thing. Oh my gosh. Recomputing height might kill performance. Dynamic array. Don't say that. Yeah. Is the height of a null subtree... So if you have a null pointer, you can consider that as long as you're consistent, you can consider a null pointer either height of 0 or height of -1. So, isn't height based on the edges between its children? So if it's null and there's no edges, it's -1. Right. So Atreus is, or Atreus, or wherever you put the stress in your name, is correct. It depends on how you define height. If you define height as in how many nodes exist on the path to a null pointer, then a null pointer would be 0. If it's how many edges exist, it would be kind of -1 in that case. Is the height being stored in the tree data structure or within its nodes? So the nodes store the height, and the reason for that is each node in the overall tree could store its height, but the height of the overall tree is going to be the height of the root node. And so it's important that every node knows its height to figure out if it's imbalanced. For this particular tree that we're learning about, though, we actually... Am I right about this? I'm pretty right about this. We don't need to store the heights at all. It's that fancy. This tree is very fancy. Please check. Thank you, Mansoor. I haven't seen that message before. I see why they call you the Menace. Okay. All right. So I don't know how many of you are Bob Ross fans, but he has specific paint color names. So that's the title of this slide. Is Bright Red or Midnight Black are 2 of his paint things. So, all right. What I'm going to tell you is we don't actually need to store the heights. Instead, we can color our nodes. We can paint our happy little tree red and black. And so each node in the tree can be red or black. And by using this color scheme, we can actually enforce this new height balance property. And we'll call it, because, spoiler alert, we're doing red-black trees, it's going to be the height balance property of red-black trees, which isn't... There's actually going to be 4 properties that we enforce, but overall, we're trying to enforce this double height situation. And we're going to do it with fun colors. Ooh. So now, think about it. What could I do if I have some tree in my head? How could I make it so that I could color my little subtree in such a way that when I need to rebalance it because it's violated this double height, double depth thing, how can I paint that subtree so that I can do these restructurings in a really like deliberate and targeted way? So I'm going to give you another hint on top of that. Let's count the red nodes as cheat days, kind of, right? So imagine that red-black trees they're kind of go to the gym. They got a gym. Red-black trees are they're the kind of trees that on January 5th, they sign up for a gym membership and they say, this year, I'm going to be a perfect tree. I'm going to be perfectly triangular. I'm going to have all the confidence of a perfect binary tree and I'm going to get that gym membership, right? And they kind of tell themselves that, but they have these red nodes and the red nodes are their cheat days and their cheat day. I'm like, oh yeah, there's some red nodes in there making me a little imbalanced. Maybe don't look at those, right? So what if we let red nodes not count against our height? Then what are we looking for? Like, how would that red-black tree cheat and allege to you that it's a perfect tree, right? What would it do? What would it say to you if you went up to a red-black tree and you'd be like, red-black tree, you're not perfect. I am perfect. No, you're not perfect. You have all that dangling. No, don't look at that, right? So we have these cheat days. So what rules would you actually, in a more mathematical and less tree-shaming way, how would you come up with rules based on how the nodes are painted red and black? What rules would you come up with to make this kind of balancing property work out with this kind of idea that red nodes are cheat days? So think on that. We're going to go back and see what how the trolls be trolling. I relate to red-black trees. Yeah, we do. Every day is cheat day during the Corona break. I like that you're saying it's a break. Cool. I like that. Kind of sounds like me. It's like, I don't know. I could have a lot of red nodes and it'd be all right. Cheating is never allowed at UMBC. I take academic integrity very seriously. I have 3 degrees from here. So, please don't cheat. Also, just don't cheat. The dangly nodes are red. See, Jeremy gets it. Whenever it's in balance, then it's red. Yeah, so you guys are kind of getting the idea, right? These red nodes are cheat days. And so we can almost think of the red nodes as like an inflammation or something like that, where the red nodes are signs of imbalance. The more red in the tree, the more imbalanced it is. So what would we say about a tree that is completely black? There's no red nodes in the tree at all. So if I'm a red-black tree, and I've actually gone to the gym, and I've not taken any cheat days, and I come back from the gym, how many red nodes are you going to see in that tree? I'm going to let the delay click in. I'm going to do some hand thing so that I can see on the stream when it's done. Yeah, big ups to Jeremy, absolutely. So, yeah, what does a well-behaved red-black tree look like? Good tree. It's balanced. Oh, Evan! It's completely balanced, yeah! It's a binary tree. Thank you, Tamar. It is a binary tree. We're not going to have a node with 3 children. A fully black tree is a good tree. It is an AVL tree if it's completely black. But we can do better. We can do better than AVL tree. It's not a perfect tree, though. So, let me go back to slides. This is awesome, by the way. You guys are killing it. Oh, Anwar! Oh, yeah. If a tree is entirely black, it's going to be perfect. If there's no cheat days, it's going to be a perfect tree. It's going to be perfectly triangular. It's going to be perfectly filled out. It's going to be perfectly balanced. Every node, its left-hand side and its right-hand side, its right subtree and its left subtree are going to be exactly the same height. And they're also going to be perfect trees. It's going to be this perfectly triangular tree. So the red nodes are where the imbalances creep in. Interesting. So this is the intuition for red-black trees, is that a perfect tree that is completely balanced and it's a red-black tree, can be painted completely black. You can put some red nodes in, but really, you could also just paint the whole thing black. So here are the 4 rules for a red-black tree, okay? So each node is painted either red or black, and then we have to follow the following 4 rules. The root must be black. Okay. I mean, there's probably a reason for that. Induction. It's for proving stuff. Almost certainly. I'm sure Professor Marin will watch this later and be like, he's wrong. There's another reason. But yeah, it's for proving stuff about red-black trees. But the root must be black. Also, every leaf must be black, and that kind of makes sense, right? We don't want our cheat days to be at the edges, and the easy way that we're going to enforce this external property is that every null pointer is actually going to be a node. And that node is going to exist and it's going to be counted as a black node. So every time every node that would have a null pointer for its left or right pointer, we're going to, for the purposes of our algorithms and talking about all this stuff, I call them fake dataless babies. And so all the fake dataless babies, all the null pointers are going to be painted black in this. And that's going to be hard to remember because when you're working with red-black trees, you have to remember that there are all of these fake dataless babies that are colored black all the way along the bottom, right? And so you kind of have to remember they're there when you're going through the algorithm for calculating how the red-black tree restructures itself. Okay. The internal property. Every red node has only black children, right? A red node may not have a red child. We'll think about that in a second. So we're talking about red nodes, we're talking about cheat days. So start thinking, why does this rule exist? Why can't a red node have a red node as a child? And think about this idea of the red nodes are cheat days, and then we're also trying to enforce this doubling situation. So why would that be the case? Why would I have this internal property? And then the depth property. All the leaves have the same black depth. This is the denial that red-black trees live in when they make their New Year's resolution, or when you ask them about how it's going and they say, "Oh no, I'm perfect. Everything's great." Right? Because what they'll do is they'll say, "Look, all of my leaves have the same depth. That means that I'm perfect." And you're like, "Wait a minute. All of your leaves have the same depth." Yeah, they all have the same depth. They're totally the same depth. That means I'm a perfect tree, because that's something that's true of perfect trees. You're like, "Wait a minute. No. You just skipped a word. You said something earlier. Oh, all trees have the same black depth. Oh. So all these red nodes. Oh yeah, no. Don't worry about those, right? So this is the depth property is also the tree lying to itself and saying like, "Oh, I'm just totally perfect." Right? So then where does this internal property come from? Why can't red nodes have red children? So let's go look at the chat and see if any of you have come up for why can't red nodes have red children. Red nodes can have children. but they must be black. Can red be turned black? Yeah, you can. Oh, Tyler's really close. For the internal property, would that mean that you have an amount of red nodes equal to twice your height? Like, we're counting black nodes only, so if we have a tree of height 4, then we need red nodes to not have red children. I think Tyler conceptually has it, and maybe, like, his wording's a little off. But yeah, think about this. So, if I have a fully perfect tree, I could paint it all black, which means that if I'm looking at the root and the deepest leaf, and I travel down that path, how many red nodes do I encounter? I don't encounter any. So then, what if I start filling in red nodes, like start painting nodes along that path red? What do we want? Well, we want, in order for this double property to be true, what is the most red nodes that we would want to see, and how would we expect to encounter them? So we're doing our sort of Wizard of Oz, follow the yellow brick road from the root to the very deepest leaf. When we're skipping along the nodes, what do we expect to see? What is the most amount of red nodes that we see? Well, if it's following yeah, Tyler's got it. Tyler's nailed it. I want to give it, yeah. When do nodes become red? Don't worry about that yet. We're going to talk about that in a minute. But in the worst case, when we're skipping down the road, we're going to go black node, red node, black node, red node, right? So the red nodes are our cheat days. We don't want to see a lot of them. And so if we don't allow a red node to have red children, that means on the worst case amount of red nodes we'll see is half of the height. That means that if we're filling in red nodes as cheat days, and we're trying to put as much cheating into the tree as possible, we're trying to imbalance the tree as much as possible, we're going to have red nodes be slotted in between every other black node, right? Because we're maxing out the number of cheat days that we allow. And so what that results in is that the height of the cheat day subtree is going to be twice the height of the fully black not cheat day subtree. And that is the little magical tricky thing that we've done to keep the subtrees within a factor of 2 height of each other, like making it sure that the one subtree is not double the height of the other. If we relaxed this constraint and we said, every red node can have a red child, but its children must be black, meaning all of the red node's grandchildren must be black, but they can have red children, then what happens? Well, if I can go black, red, black, red, black, that now is meaning that I'm letting one of my subtrees grow to be 3 times the height of the other subtree, which is, that's a slippery slope. And if we didn't have this rule at all, then we could just say, then our red-black trees could really lie to us when they came back from the gym. Oh, how's it going? Oh, yeah, it's going really great. Yeah, look, you see all of my leaves have the same black depth. That's cool. This whole subtree is red. All of it's red. You're not very balanced. Like, don't judge me, right? So you have to have this limitation in there to keep this doubling situation happening. All right. So Tyler nailed it. Tyler gets I don't even know how you there's those little you can heart someone's comment. Oh, can I do that? Is that a thing? Put user in time. No, I don't. I can't do any of that stuff. I'm not going to make Tyler a mod, even though I'm sure he'd be a wonderful mod. All right. Okay. So how do we do this? How do we do insertion? And to Anuar's question, how do we figure out which nodes are red? When do we make nodes red? When do we make nodes black, right? We've kind of come up with a set of rules to play the game by, but now we need to come up with a strategy for inserting and removing nodes. And I'm going to tell you that there's a reason we do 2 lectures on this, because it's complicated. In fact, how am I doing on time? Okay, awesome. So, what we want to do. So I'm going to go through this procedure real quick, and then I'm going to like intuitively motivate it in terms of like cheat days and so on and so forth. So we're going to insert some value with key K. And so for binary search trees, we only really care about the key for doing the comparison. So we find the spot at the bottom of the tree and create a new node there. So first of all, when we're reading this, we have to think, why is the spot at the bottom of the tree? Well, if you remember from doing all those, like the practice and the exercises, is that whenever you put a new node into a tree, you're going to start at the root and you're going to do comparisons until you find a null pointer somewhere that you can then stick that new node into. Now, when we were doing AVL trees, once we put that new node in, we climb back up and find our crazy imbalanced grandmama Z, and then if we found her, we would do some restructuring. So now what we're going to do instead of that is we're going to go down at the bottom and we're going to pop the node in, and then we're going to make it red. Why red? Well, because red lets us be lazy. Because we're developers. We don't want to do work. We want things to just kind of like be okay. So what we're doing is when we go down there, we're inserting that node and we're coloring it red because we're like, let's just make it a cheat day. And if it's allowed to be red, like say its parent is black, then we're done. And I like being done. I like being done immediately. I love it when there's no task better in the world. When you guys are software developers, you're going to love this. When somebody comes to you and they say, hey, I don't know how hard this is. They always start things with, I don't know how hard this is. I don't know how hard this is, but could you do blah, blah, blah? And you'll sit there and you'll be like, yeah, that's real hard. I'm going to need a few days. I have to really think through that and design it. And what they just asked you was basically for a feature that you were using to debug the code you wrote at that point, and you just have to like turn a knob. But you have to be good at managing expectations, so you have to say, like, you have to always tell them that everything takes a little bit of time. And it's true, it does, because you have to flip that switch and send it to the testers and make sure that everything works. You're not lying, but it is a good feeling to be asked to do something you've already done. So when I insert that red node, getting back to the point, when I insert that red node, I might have a case where its parent is black, at which point I'm just done. That's awesome. We're also, when we make that put that red node in there, we're going to make its null pointers black for our purposes. The other way to think about it is just every time we see a null pointer, we count it as a black node. So you don't actually have to fit the black nodes into the tree when you're implementing this. You can make like a special node that has like a null value or something like that, or a flag on it that says I'm actually a fake dataless node, and then set it to black and so on. You can do that, but you can also just say, every time we see a null pointer, we pretend that it's a node that contains no data that is colored black. So are we good? Are we good? Are we done? Probably not, right? Because I've been saying how annoyingly complicated this are. Why would this be a problem? Well, if we're only inserting nodes and we're coloring them red, if that's our algorithm, we just color them red immediately. Well, what's the problem there? Well, if every new node that goes into the tree is red, we're very quickly going to have the case where I've inserted a red node underneath of a red node, and that breaks our the internal property. And I had to go back here to show it to you to remind you, but I also didn't remember the name. I guess you could make it like, it's ride, root, external, internal depth. But yeah, so we've broken that yellow brick road, that cheat property, that we've cheated too much. If we put a red node underneath of another red node, we put too many red nodes in. And so then what do we do if it's a red under a red? What if its parent is black? If its parent is black, we're done. So that's great. I'm going to go check for questions. I'm only going through too many slides without. Boop. What you're saying is you can have a fully black tree on the left of a root of height 3 and an alternating red-black tree on the right with a height of 6. That's correct. And so if I have a node, I could have an entirely black subtree on one side, and then in the worst case, the most imbalanced version on the other side would have a path to its leaf that alternates red and black on the way down. That would be a worst case red-black tree, where one subtree is fully black and the other subtree has a path that's zebra striped all the way down. Now, they don't all need to be zebra striped, right? But we're talking about a worst case, so there has to be at least one path that zebra stripes all the way down. Good question. Or comment. No power would go to my head. I'd be a terrible mod. Oh, the power would go to your head. Yeah. You start banning everyone. Oh, Min will be a mod. Min's a mod for everything. Min, you can be a mod. So Min's a TA and also been helping with the Discord bot, and we're super grateful. And now he's been made a mod. With the fake data, how would the fake dataless data work? Would you just skip past them when making a new node? When you're making a new node, you'd actually be looking for one of the fake dataless leaves, right? Because when you're doing an insertion, you're looking for a null pointer. And if we go back to our code, actually, let's do that. Go back to our code. It's not here. It's not. Oh, okay. Wait, what? This is the exam question. Oh, yeah. So here's the exam question answer. This is what I was looking for. Actually, I think I was looking for another null pointer, but I write them just to make sure that my test outputs are correctly. But you should also check. Oh, no. This one still works that way. But there's the exam question. That would have sucked if I hadn't given the exam yet. Haha. I still have a couple of makeups, but they'll be getting a different exam, and they really will now. Okay, BST node .h. Wait, we're in BST node. So here's our insert, remember? We're going down here, and we're looking for this null pointer. So if you were actually modeling the fake nodes, what you would do instead of this null check is you would ask if left or right are null, like have their little null flag set to true, and if they did, you would delete them and put this new node in its place and give it to fake nodes. The thing is, you don't actually have to use the fake nodes as long as you count every null pointer you see. You can use a normal binary search tree, except that when you see a null pointer, you count it as black. Okay. And this is really hard to do without a whiteboard. Another thing that I'm working on. Well, I'm going to be able to draw soon. Okay. Oh, let's see if there's any other questions. How about me? I'll definitely not remind you to please check the video resolution. Okay. Thank you, Mansour. You're very helpful. I know it's not ideal, but it's what my display does. Okay. So we might have a double red. So now we have a new algorithm, and this is the letters that we're getting here are from the textbook. But we're looking at our aunt, W. Our Auntie Dubs. Love Auntie Dubs. She's the cool aunt. So we look at Auntie Dubs. How do we find our aunt? Well, I can draw with, so I think I'm going to pointer. Ooh. Can I draw with this? No. Whoops. Hold on. Please wait. Learning how to teach. Okay. Is this pointer visible? All right, well, you guys tell me if the pointer is visible. Is my mouse visible? Oh my God. Okay. Sorry about that. Oh, I also didn't make the sea lion larger. The point from the I'm gonna make it larger now. You won't be able to see me doing that, but come on. It's okay. You can do it. Increase. Enhance. Enhance. Okay. Oh, I have to undo it one more time. Enhance. Okay, cool. Excellent. Okay, back to the slides. Okay, now you should be able to see a pointer, hopefully. So here's the case. We're looking for anti-dubs. Anti-dubs is if I put in a node and my parent is red, that's problematic, right? So remember, if I put in a new node and it's red and my parent is black, we're good. We're totally good. But if I put in a node and my parent is red, that means we have a double red and we violated the internal property. In which case, there are two cases for insertion. One case is if anti-dubs, our cool ant, is black. If W is black, then we do a trinode restructuring, where the Z, the grandmama Z, is the grandparent of the node I just inserted. So we're just doing this little operation on the subtree. And so we can see that if we have a tree like this, we're going to do this trinode restructuring so that now everything's going to be shifted over. Then what we do after the trinode restructuring, the new root is black and its children are red. And so that's how we repaint things afterwards. So Anwar had the really awesome question earlier of when do things become red and black and so on and so forth. So every node goes in as red, and then during these insert and remove algorithms, we're going to be repainting things. And so repainting is a bit faster because you don't have to do all these pointer swaps and things like that. It's still not asymptotically faster. They're both constant time. But flipping a Boolean on a node is much faster than doing a bunch of swaps in a constant time sense. It's also, yeah, it's the constant that we ignore for big O is smaller in that case. Oh no! What if anti-dubs is red? Well, we can recolor without having to restructure. So that means I can take my aunt and my mom and I can color them from red to black, and then I can make my grandparent red now. Are we good? Fun fact, I don't remember. So, I don't remember. Are we good? So let's think about it, right? Let's look on this left-hand side. First of all, I'm going to check OBS to make sure I am actually streaming. Okay, cool. And I'm going to check your comments to make sure you're not, oh my gosh, everything's broken. Stream is fine. How do you know which color to repaint them, though? It's just prescribed by the algorithm. So the trees go in red, and our procedure dictates that you do this swap-a-roodle. And if you think about it, we're taking the justification for this. I don't know if you guys can see my pointer. Somebody should tell me yes or no on the pointer in the chat, so when I look back, I can know whether or not. But if you look at these four nodes and look at the black nodes that come out of this, right? So we have W, the children of Z, and the children of V. And so what we want is we want their black depth to be equal after the trinode restructuring. And so the way that we can do that is after the trinode restructuring, we make the root black and then the two children red, and then so everything will be kind of okay for that. The thing is, yeah, that makes sense. And V's other child has to be black, because if it were red, then we would have already had a double red that we should have fixed. We're always assuming that we're inserting into a valid red-black tree. So then are we done here? So the question is, these things had a black depth of 1 at this root. Then what I did is I added a black depth to all of these nodes of 1. So this subtree, these fake dataless babies down here, gained 1 black depth. Is that okay? Well, it's okay for the subtree, but what about the rest of the tree, right? Like, you will have ancestors and stuff like that. So I've increased the black depth, potentially. Oh, no, wait. No, I haven't. No, look at that. No, I haven't, because I took this black node and I pushed it down. So actually, I have not changed the black depth, which means I should be good. Hopefully, he clicks. Yeah, we're good. Great. So now it's Would You Rather time. Yeah. Again, these aren't as fun in class, but start shooting me questions about this one. The Would You Rather is, I love this Would You Rather. Would you be able to slap anyone on the face? And on the face is emphasized because I usually get the question of, do you have to slap them on the face? And I'm like, oh, yeah, that's... be able to slap anyone on the face and everyone in present, including the victim, thinks it's hilarious. Like, oh, ha, 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 that's funny. Anyone. You can slap anyone. Everyone thinks it's hysterical. No matter how many times you do it, they think it's hilarious. As long as you don't physically harm... If you get so strong that you're knocking people unconscious, that's maybe not as funny. Or you are worshipped within the political boundaries of Erie, Pennsylvania. The current ones. Because I always get the question, oh, well, can I have my followers in Erie, Pennsylvania go, like, take over other towns? No, it's the current ones. So you're worshipped in Erie, Pennsylvania, or you can slap anybody and they think it's hilarious. So I'm going to go over... Also, if you keep popping red black tree questions in there, this is the insert procedure, by the way. This is totally the insert procedure. So if we do the trinode restructuring, we're done. And if we do this recoloring, we're done, I think. Yeah, we're done. Cool. Someone's going to tell me we're not done. I'm going to be sad. In fact, I'm going to go look at the cheat sheet because I feel like that's not correct. Boop, boop, boop. Being prepared is good, but I have a lot of things to do. Red black cheat sheet. So here's the red black cheat sheet. As you saw, it's in with my slides. Again, you will have this available to you on the exam. I'll either be included on a packet or I'll project it up on the wall. This time I'm definitely going to include it in the packet because it is 2 pages. And also, because they're red black trees, having color is, well, nice. So you will be allowed to bring your own from a color printer as long as you bring them up and show them to me that it's, like, colored correctly. Okay, so yeah. Oh, right. This is why you might have to possibly repeat. So in addition to the would you rather, also think, why would you have to repeat this recoloring procedure? Why would you have to repeat that? All right, let's go to the comments. People are going slap. Start a cult in Erie. It wouldn't even be a cult. They would just worship you. Root needs to be black. So inserting, we always assume that the node will be red, and then we update it to black if no restructuring is needed. Good question, David. So what we do is we insert the node all the way down at wherever, like we find a leaf, the spot where that node would belong, we insert it as red. If its parent is black, we're done. If it's the only node, we change it to black because the root has to be black. And that doesn't break any of our properties. We're allowed to do that because it keeps the black height the same, and it also allows us to adhere to the root property. Awesome question. But yeah, when the node goes in, it's red. If its parent is black, you're done. If its ant is black, you do a trinode restructuring. And if its ant is red, you do a recoloring process that could potentially repeat. And the current question is, when would you have to repeat it? So we've already established that I haven't upset the black height, but what other property of a red-black tree could we have violated with that recoloring procedure. Please say we are good. No. Doesn't the root have to be black? So it's not good. The root cannot be red. The root has to be black. So if you insert, the first node that you insert goes in red and then immediately becomes black. So you just flip it. Because you're like, oh, this is the root, so it should be black. But for every other node, it goes in red and then you follow the insertion procedure. But why do we have to repeat the recoloring, possibly? How are red and black stored in the node? Are they strings or a different data type? You can use a boolean and just say is black or is red. You could use an int or an enum. However, you could use strings. That's a little memory hungry. Yeah, boolean flag. If these are subtrees, then the red node isn't the root. Absolutely slap. I can't get on Prof.J's websites to view slides. Anyone having that issue? Is our CS page down? That would be great. It's up. The URL is here. Let me drop that into the chat. These are great. I love the conversation. Tyler has an Amish army. Oh no, okay. What's the population of Erie, Pennsylvania? I don't even think I have to look this up. I think the last time I looked, it was 98,000, roughly. Erie, PA, Wikipedia. Show me 98,000. Oh, if I'm right, I'm going to be so happy. Oh, 101. Wait, the estimate is 96,000. Anyway, I was really close. I probably would have, if that were Price is Right, I would have nailed it. All right. 97,000. Oh, it was right in the chat. 97.3. Slap, you get away with anything. This is supposed to be a brain break. Sorry, Jeremy, I've tainted your brain break. Repeat when the root is red. So the exam's still being held at UMBC. Yeah, we're going to probably have to do something different than a standard exam. That's still being sorted out. For this class, I'm leaning towards take-home exam. That'll have like a pretty tight deadline on it, but I don't know. Don't know yet. Still working on it. I'm going to poll the other professors and see what they're doing. Kevin, can I get one? I'll pay. No longer an issue. No, just... Okay. All right, cool. How... Oh, is there a way to do a poll? Crap. Quick polling. Fast poll. Create my poll. Yeah, cookies, sure. I love cookies. What's your favorite color? Slap or Erie? Option 1, slap. Option 2, Erie. Add another option? I don't even want that option. Why is this red? Why are you mad? Oh, it's the option color. Fine. Go. Allow multiple votes. No. Enable CAPTCHA. What? This is too fancy. Category web design. Let's say animals. It seems right. A poll's been created. Oh, excellent. Let's put the poll on the internet. Boop. There you go. Fast poll it. Let's see how this would you rather balances out. Now I'm going to have actual quantitative data on this would you rather. It's very exciting. Any other questions about the would you rather? Our schedule has Project 0 and Project 1 through 4 for the grading, but there's a Project 5? Oh, okay. So that in the class schedule is old. There will not be a Project 5. That was the time I was going to use to talk about Project 5. Instead, we might get a bonus lecture. I might go more into graphs or some other fun data structure. Very exciting. Whatever you do, don't make anyone use that lockdown. Yeah, no malware. We can pinky promise not to cheat. Also, the lockdown browser can't stop you from having a laptop right there. It's like, we're gonna have you lock down your browser and you still have a phone. Like your friend who's on another computer. Like, come on, that's silly. No, an unbreakable spell. You lose your pinky. It covers your whole face, so you walk in the store and it looks like you're about to rob it. Oh, should I accept cookies? It's trying to give you cookies, Mansour. I usually tell you not to accept cookies from strangers, but I think this one's okay. Take the cookies. All right. Nobody's had questions. So, some questions I usually get about this one are, can I extend the political boundaries of Erie, Pennsylvania? No. Can I knock someone out with a slap? If you hit them so hard that they lose consciousness, it's not funny anymore. So you have to learn to, like, manage your slap strength. If you happen to be a very strong human. Anyone, as long as you get access to them. You might still be in trouble for trespassing, but people be like, it was really hilarious, but you're still going to jail for going to a place you're not supposed to. So, but no one will consider it assault. Everyone will think that it's hilarious, as long as you don't, like, actually physically hurt them. And I should also say that I in no means condone physical violence in any way. This is just a very hypothetical situation for those of you watching in the future. It's just for funsies. It's just a fantasy scenario. I'd be benevolent, wise ruler. Tyler is probably already on Google Maps picking out where his house or palace will be in Erie, Pennsylvania. Fun facts about Erie, Pennsylvania that I just remember from having to do this Would You Rather a few times. I believe it's equidistant between Cleveland, Ohio, Buffalo, New York, and Pittsburgh, Pennsylvania. 3 cities that are fine as well. It's like, oh, I'm at the epicenter of, sure. I mean, all right. Oh, so the people will be obsessed with you and worship you until they cross the boundary, and then they'll be like, I don't really get it. What was that about? And then as soon as they come back in, they're like, oh no, Tyler's great. Any other questions I usually get about this one? No, I think that's pretty much it. Natalie, do you have any questions about the Would You Rather? Oh, you're all right. Also for the brain break, I got my sleepy cat. Oh, there he is. He's very big. Oh, he's gonna sniff stuff. Oh, you're very warm. We'll see how long he hangs out with me. Okay. Someone's doing Far Cry 5. Oh, in real life. I was like, are you playing Far Cry 5? I mean, I guess that's fine. I can't... You're not distracting anybody. Anyway. Cool. Make it a tourist trap and then keep them there forever. Yeah, you guys get... Comp sci students get really dark with this one. You could be like, oh, and if I'm worshipped, then I'll build this beautiful humanitarian utopia. Somebody always takes it kind of in a dark direction. All right, cool. Any other questions? All right, we're going to go to the poll. I don't know what the results are. As Jules leaves, it smacks me in the face. Jump to results. Oh, damn, this is a good Would You Rather. 53% vote Erie, Pennsylvania. 48% vote slap. Okay, well, I might check on this later for those of you viewing it at a different time to see how it's gone. It might be really Project 3 is probably coming out later today. We've been very busy shifting our classes online, so the Project 3 will come out. I know you guys are really excited to see Project 3. I am too, actually. It'll be fun. Very difficult, but fun. All right, so here we go. What time is it? Yeah, so I'm going to wrap up soon. So the brain teaser... The brain teaser is, are we good now after we do this? So if I recolor you to red, why would I not be done? So let's go back and look at the properties. So U was the root of my subtree. So could I possibly have violated the root property by making the root of a subtree red? Yeah. Uh-oh. Gross. So if the root of the subtree is red, if the subtree is actually the whole tree, right? And I've just now made the root red, uh-oh, what do I do? So the panic anxiety part of our brains might be like, oh no, we're gonna have to do like some other restructurings and oh, it's gonna be a mess. Well, it turns out, as you're kind of flipping the colors, because you think about it, we kind of have this zebra stripe thing going on over here on the right-hand side in the product. And what we're doing is we're just kind of flipping the zebra stripe thing up, all the way up the tree, if we repeat this procedure. Which means that if we get to the root, and the root is red now, everything underneath of us, our left subtree and our right subtree, are valid red-black trees. And this can be proven. You can convince yourself of this when we start doing practice, which is going to be weird because we don't have the board games. When we start doing, I can't even go to my office to get it because they're like, don't come in unless you have very serious business. So I'm going to have to make one. That'll be fun. And rig up a way to show it to you. But anyway, as this zebra stripe gets moved up, if the red node, if the root has been colored red as a result of this procedure, then its left subchild and right subchild are valid red-black trees, meaning that all of the leaves, all the fake dataless black nodes, have the same depth, same black depth, which means if we take the root, which is red, and add 0 to the black depth and flip it to be black, then we're good, because I've just increased all of the leaves depth by 1, and I've increased all of the leaves depth by 1. So if they all had a black depth of 3, if I change the root from red to black, they now all have a black depth of 4. So I'm increasing all of their depths uniformly. And so that's a way to deal with, if I've colored the root red, I can just flip it to black. But there's another property that could be violated here. What is it? What's the other property that I could have violated with this insertion? Is it the depth property? I'll give you a clue. It's not the depth property. We already kind of talked that out, right? So if we look at the black nodes that are all children of these red nodes, after I do this recoloring, their black depth is the same, because they had, in the circled area on the left, they had one node they had one black depth, and in the circled areas on the right, they have one black depth. So I haven't changed their black depth, so I'm okay about the depth property. So what about the external property? Have I changed that? No, we enforce the external property by saying all null pointers are black. So then it's the internal property we may have violated. So before this, U was black. The root of the subtree was black, which means it could have a red parent. It could also have a black parent. It's fine. Black nodes can have black parents or red parents. But it could have had a red parent. So when I do this recoloring, I'm changing U from black to red, which means if this subtree was stuck underneath of a red node, now I have the double red problem again. And I've pushed the double redness up the tree. So now what I do is I repeat this procedure, except I'm starting at U now because it's the bottom of a double red. And then I'm going to look at anti-dubs. And if anti-dubs is black, I do a trinode restructuring and I'm done. And if anti-dubs is red, I recolor and possibly push... basically, you're pushing the redness up the tree. You're floating the redness up the tree. And so when you do that, eventually either you're going to hit a trinode restructuring and be done, or you're going to push the redness all the way up to the top where you'll have a root that's a red node, and then we can flip it black and we're done. And that's insertion in a red-black tree. And I'm going to remind you that the trinode restructuring, the thing that was hard about AVL trees, is just kind of like a little step. It's a little like, oh yeah, just do that in here. So red-black trees are generally more difficult because the procedures have like the hard part of AVL trees as like a little sub-step. That's like when you're cooking and you pull out a recipe and you're like, oh, I can make this steak or something or whatever. I'm going to make this korma dish or whatever. And it's, oh, look, it's only 3 steps. I can knock that out pretty quick. It doesn't seem that complicated. And then you go down and you get out all your ingredients and you look at the recipe and then you're like, oh no, because step number 3 is prepare this sauce. And then you go to another recipe and it's like 80 steps. So that's kind of how a red-black tree is that some of the sub-steps are like conceptually still pretty difficult things. So I'm going to pop over and see if there's any questions. Everyone said internal property. Very like Shadow the Hedgehog. This is serious business. I'm going to check on the poll again. Can I refresh? Ooh, it's still sticking to 52 to 48. Good stuff. That's a strong would you rather then. All right, well, I think that's it for the day. That's a 75-minute lecture. I have a delicious beverage. I'm going to sit around and look for questions for a few minutes. But if you're here live, go away because we're done. Or ask questions or hang out and chat. If you haven't gotten on the Discord yet for this chat, we'll be doing office hours on Discord. I'll be doing my office hours at 4 o'clock today on Discord. And I'll be in the general chat there telling you how I'm going to run those. If you're having problems getting into the Discord and authenticating with the Discord, you can email me or message me in Discord because you'll see me on the right-hand side. Prof J will be over there. Wait, right-hand side. You'll see me over on the right-hand side in Discord. So give me a hoot if it's not working. The bot has been under. It's very beta right now. But yeah, I'll be holding office hours at 4 and in Discord. There's no project out and there's no homework out. There'll probably be a homework out for our section very shortly. But yeah, I don't see a lot of you guys coming to office hours unless you want to like talk about birds. Bye, Will. It's supposed to be Corona only this semester. Dr. Pepper, the drink of intellectuals. That's right. Don't drink Mr. Pibb. As Mitch Hedberg said, dude didn't even get his degree. Okay. All right. So, how do you think it's affecting the sale of Corona beer? I would actually like to think that it's increased the sales of Corona beer because there's no such thing as bad advertising. Should we give the link to the CMSC Discord as well? You're welcome to. There is a Discord for just the computer science department. And it's been around for a while in a sort of like capacity. You can go on there. Again, there's professors on that Discord. The professors are going to be monitoring the Discords for their respective classes much more intently in terms of giving out help. But you're welcome to go on there to chat and kibitz. As always, adhere to the academic integrity policy. Do not post code for your assignments on that Discord, or the mods will come down on you. It's pretty tightly modded, so don't do that. It's not cool. That Discord is generally pretty awesome, though. You can get career advice. You can meme it up in a different meme zone of memery. You can memulate, or however the memes get memulated these days. I don't know. I can't hashtag the social medias very well. Minecraft live stream when? So Ben Johnson NLP is my like little YouTube channel. I'll be putting both my 341 and 201 lectures on here, and I'll be doing, as a brain break for 201, the 201 TAs. I've set up a private Minecraft server for them, and we're going to do little tours of the stuff they've made. So I have not had the time to Minecraft. It's also been years since I've done any Minecraftery of my own. I've challenged them to build like an adder out of redstone, though. Yeah. All right, guys. Have a good Monday. Stay occupied. Behave yourselves. Probably going to be pretty prolific on Discord. I'm still really bummed that we don't get to do board games and stuff like that, but is the difficulty for the level for the project staying the same? No. Usually Project 3 is harder. We don't intentionally, we're not like, oh, we're going to give it to them on Project 3. We're going to make that one really hard. That's not the idea. It's just the subject matter for Project 3 is this is the first time you're getting a project that's really just 341 material. So Project 0, 1, and 2 are kind of review in nature. Like you're doing linked lists, you're doing array stuff and queues and all that other good stuff. But trees, you guys probably haven't been hit with like a big, computer science project around trees. You might have done exercises on trees. We've done live coding, but doing a big 341 project on trees is going to be more difficult, just by the fact that it's the first project that isn't review. So, and I forget what the topic listed for Project 4 is. I believe it's heaps and or hash tables. So that'll be fun. Lots of trees. Can we get a Minecraft server? No. I mean, you can set up a free one. You guys already have Minecraft servers, I'm sure. Was Twitch an option to stream, or did you choose YouTube because of access? So I thought about Twitch. I'm using OBS, so it's trivially easy for me to use Twitch. Then you guys get better emojis, which are, great. But what I really like about YouTube is that you can rewind while it's happening. I don't think you can do that on Twitch. So if somebody comes in late, they can just start the stream from the beginning. And then also it's just posted indefinitely as a video. Whereas I think Twitch, you have to be like, you have to do something special either with money or clicking of things to get your video saved. So yeah, Min just completely said what I said. So you're going to get to hear me say what Min said in like 2 minutes. Be down for a CS Minecraft server. I was ready with the Twitch Prime. Thanks, but I can't imagine it's even vaguely legal for me to accept that. But I'm flattered. If you do this in chat, the chat would just be Pog. Yeah, I know. Oh yeah. I don't know how I can enhance the emojification on this, but anyway, I didn't know YouTube had a Kappa emoji. Does it? Oh, is that what Kappa is? That little, like, smarmy dude? Anyway. Alright, guys. Have a good Monday. Bye.